You're sitting in seat 14F. You hear the chime, the flight attendants take their seats, and then comes that unmistakable surge of power. The engines roar to life, your back is pressed into your seat, and the world outside the window becomes a blur of gray asphalt and white lines. For you, it's just the start of a vacation. But for the two pilots in the cockpit, this is the most demanding, high-stakes moment of the entire journey. In the next 60 seconds, they will manage hundreds of tons of metal, fuel, and human lives as they transition from the safety of the ground to the unforgiving physics of the air. This isn't just a drive down a runway. It is a calculated leap into a realm where the margin for error is measured in split seconds. In aviation, we often say that speed is life. During takeoff, the airplane is in a state of vulnerability. It is too fast to be a car, but too slow to be a fully stable flyer. It is transitioning between two worlds. While cruising at 35,000 feet is relatively relaxed, takeoff requires the aircraft to operate at its absolute mechanical limits. The engines are at maximum thrust, the tires are spinning at their highest rated speeds, and the wings are struggling to find enough grip in the thick, low-altitude air to lift the massive weight of the plane. It is a symphony of engineering where every instrument must play perfectly, or the conductor must know exactly when to stop the show. One of the primary reasons takeoff is so critical is weight. When a plane takes off from an airport like LAX or Chicago O'Hare, it is at its heaviest. It is carrying its full load of passengers, cargo, and most importantly, thousands of gallons of jet fuel needed for the hours-long journey ahead. Because the aircraft is so heavy, it requires an incredible amount of energy to get it moving. This means the runway must be long enough, the engines must be healthy enough, and the air must be cool enough to provide the necessary density. Unlike landing, where the plane is much lighter because it has burned off most of its fuel, takeoff is a test of brute force against gravity. Pilots don't just guess when to pull back on the stick. They use a precise set of calculated speeds known as V-speeds. Before every takeoff, the flight computer calculates these numbers based on the plane's weight, the wind, and the temperature. V1, decision speed. This is the most famous number in the cockpit. It is the point of no return. Before the plane reaches V1, if a pilot sees a warning light or hears a strange noise, they can slam on the brakes and stop the plane safely on the remaining runway. VR, rotate speed. This is the magic moment where the pilot pulls back on the yoke and the nose wheel leaves safety speed. This is the speed the plane must reach to ensure it can still climb safely even if one engine fails completely. The concept of V1 is what makes takeoff so psychologically intense for pilots. Once the V1 callout is made, the pilot's hands move away from the throttles. Even if an engine catches fire or a tire blows out after V1, they must take off. Why? Because at that speed, there simply isn't enough runway left to stop 200 tons of moving metal. Attempting to brake after V1 would lead to a runway excursion. The plane would go off the end of the asphalt. In aviation, it is often safer to take a damaged airplane into the sky where you have space and time than to keep it on a ground that is about to run out. While you hear the roar of the engines, what you are actually hearing is a machine fighting a war against heat. To get a heavy jet airborne, the engines must produce maximum rated thrust. Inside the core of the engine, temperatures are reaching nearly 3,000 degrees Fahrenheit. The turbine blades are spinning so fast that the centrifugal force is trying to pull them apart. This is the only time during the flight where the engines are pushed this hard. If a mechanical flaw exists in the engine, it is most likely to reveal itself during these first 2 minutes of maximum stress. This is why pilots keep their eyes glued to the engine gauges during the roll. They are looking for the slightest hint of a hiccup before they hit that V1 commitment. The most dreaded scenario for a pilot is an engine failure at the worst possible moment, usually right after the nose lifts off the ground. In the US, pilots are tested on this in simulators every 6 months. If one engine dies, the plane will suddenly want to yaw or swing violently toward the dead engine. The pilot must immediately use the rudder to keep the plane straight and maintain a precise pitch to keep the speed at V2. It is a high adrenaline balancing act. Modern twin-engine jets are designed to be able to climb out safely on just one engine, but it requires the pilot to be perfect. There is no room for hesitation when you are only 100 feet above the ground. Because the workload is so extreme, the FAA enforces what is known as the sterile cockpit rule, FAR 121.542. From the moment the plane starts taxiing until it reaches 10,000 feet, the pilots are forbidden from engaging in any non-essential conversation. There are no jokes, no stories about the weekend, and no small talk. Every word spoken must be related to the takeoff. They are verbalizing, the flight calling out speeds, checking flap settings, and confirming gear retraction. This total focus ensures that if something small goes wrong, it is caught before it becomes something big. In these few minutes, the cockpit is a temple of concentration. You might think landing is harder because you have to hit a specific target. But in landing, the plane is light, the engines are at low power, and if the pilot doesn't like the look of things, they can always go around, climb back up and try again. Takeoff doesn't offer a do-over. You are moving from a state of zero energy to high energy. You are fighting inertia. You are battling gravity with a full load of fuel. If you lose power during a landing, you're already close to the ground and slow. If you lose power during takeoff, you are heavy, low, and struggling for speed. The margin of safety is at its absolute thinnest. Fortunately, we live in the safest era of aviation history. Modern planes have auto-throttle systems that can set the exact perfect thrust for the conditions. They have performance computers that tell the pilot exactly how much runway they will use down to the foot. We also have EMAS, Engineered Materials Arrestor Systems, at the end of many US runways, specialized crushable concrete that can stop a runaway plane safely if a pilot has to abort a takeoff at high speed. We have engineered the risk out of the takeoff as much as physics allows. So, while you're looking out the window, noticing the wings flex as they grab the air, remember that you are witnessing a managed miracle. Takeoff isn't just about going fast. It's about a complex set of if-then decisions being made by two highly trained professionals and a suite of computers. They have already planned for the engine failure, they have already calculated the stopping distance, and they have already committed to the sky before the wheels even leave the ground. In just about 120 seconds, the airplane goes from a heavy, grounded object to a soaring machine. It is a transition of power, speed, and precision. It is the moment where the genius of human engineering overcomes the stubborn pull of the Earth. Takeoff may be routine for the millions of people who fly every day, but it remains one of the most incredible things humans have ever taught machines to do. If you've ever felt that rush of adrenaline during takeoff, now you know why your body is sensing the extreme physics at play. If you want to dive deeper into the world of V-speeds, engine thrust, and the secrets of the cockpit, make sure to hit that subscribe button. Join us as we demystify the sky, one phase of flight at a time. Thanks for watching Aero Explained, and we'll see you at cruise altitude.